Yeah, so it has started recording. So let's start the class. So we did not. So today is Wednesday. We met last Wednesday, right? Last Friday is when I canceled the class. No, is that correct?
Yes, sir.
Yeah, last Friday we did not meet, so we had a long gap, and we had finished chapter 1 of Rudin. We are going to start chapter 2, and maybe I mentioned that in chapter 2, what is the most important result that we will do? Do you remember the name?
Almost everywhere.
No, that was chapter 1. In chapter 2, I might have mentioned one name. No one, there's a very famous name theorem, very important result. Does anyone remember? Yeah.
Representation.
The Rees representation theorem, which we will not start today. We will start in the next class. It may require more than one lecture to do it, but we will start in the next class. Okay. So what we will do today is some basic topology, which you already know. I will just recall. Okay, so that's the plan. So let me start sharing the screen. And one of you can confirm that you can see the slides.
Yes, sir.
Yes, sir.
Okay.
Yes.
You know. Okay. So today is what we are going to do is towards RRT. RRT is what? What is RRT?
Rees
Rees
representation.
representation theorem. And towards. So we are not doing it today. We are doing some preliminaries, topological preliminaries, which you might already know from your topology course. We will recall. And the idea is to start the proof of Rees representation theorem in the next class. Okay. So let's start by recalling what we did up to now. So last to last class, this is uh, lecture 3. What did we do? We proved these famous results, MCT, that's monotone convergence theorem, Fato's lemma, and dominated convergence theorem. So very quickly recall, MCT and DCT, you said that if you have a sequence of measurable functions, then the limit is of course measurable, and integral of the limit is limit of the integral under some conditions, right? In MCT, the conditions were that the functions are monotonic and valued in 0 to infinity. And in DCT, what was the condition? All these functions are dominated by an L1 mu function, an absolutely integrable function g, in which case also you can interchange. Okay. And in the last class, we discussed the role played by sets of measure 0. So this was the last part of chapter 1 of Rudin. And we did several small things. In particular, there were two results which I stressed a lot. Can you recall? One result had a name, other result did not have a name, but I connected it with some other name theorem. Can you at least tell me the names? What was the named lemma that we proved? Yeah? Just give me the name. I am not asking for the statement.
Sir, average
Borel-Cantelli theorem.
Yeah, one is Borel-Cantelli lemma, and the other is, yeah, what you said, average. Something about average, right? And it did not have a name, but I said this result will play a role in some other theorem later, no? Can you recall?
Yes, sir. Radon-Nikodym.
Radon-Nikodym theorem. So what was the statement about averages? What was the main assumption? Was it for any measure space, or there was a condition on the measure space?
Finite measure.
Finite. So if the space is finite, and then you have a closed set, right, in complex numbers. And then what did we say? If all the averages belong to that set, then what is the conclusion?
And the function valued on that set.
Not always.
Almost everywhere.
Almost everywhere, right? Almost everywhere. So proof was not very difficult. And what did we do in the proof? We have to show that the set where, yeah. So you have this set which we call S in complex numbers, and we have to show that inverse image of the complement of S, right? Inverse image under this function of the complement of that has measure 0. And what was the main idea of the proof? because it's a closed set, it's complement. The first thing was to say that it's enough to do for closed balls in the complement. Is that correct?
Yes.
Yes, sir.
Yes. So we might have denoted it center alpha and radius r or something. Was that the notation? Alpha and r, is that correct notation? I'm just trying to recall. I also have forgotten. So so you have a closed ball alpha comma r. If you take that, you have to show that the
That
inverse
set has
image of
measure zero.
that, right? Inverse image
Yes.
of that. Are we going to claim that it has measure 0?
Yes.
And what was the main idea?
Yes, sir.
By contradiction.
Yes, so we took average minus alpha the modulus of
Yeah.
average minus alpha.
Yes.
That looks correct because average of this function f, right? So average of f minus alpha. Now alpha also can be written as alpha times integral d mu by mu of e
Me of you.
because of finite measure, right? We are assuming mu of, yeah, correct. So therefore this difference, yeah, this difference you can analyze and then you will get a contradiction. Okay, right? This difference, absolute value of this difference you can analyze and immediately you will get a contradiction. And the contradiction is because you assume that the measure is positive, right? So therefore the measure is 0 and that is the thing. And I said that this will play a role in the proof of Radon-Nikodym theorem. And what was Borel-Cantelli lemma? Did we have an assumption on the space, finite measure or something? No, we did not require that. But what was the hypothesis? What is a hypothesis and what is assertion? Assertion is that a certain set has measure 0, right? I mean, we reformulated in terms of, you remember, lim sup of a sequence of sets. We define, no, the limit superior of a sequence of sets, and the assertion was that mu of lim sup is 0. But what was the hypothesis? So you have this collection given, if you call it AN. What was the hypothesis on this collection?
Summation of measure mu of En should be finite.
Yes, if that is finite, then mu of the limit superior of this sets, that is 0. And what was the main idea here? What was the main idea? Yeah, summation mu an is finite, right? That is what is given to you. And did we deal with characteristic function? How did we do this? So summation mu an, in order to get that, that is same as, so we use this fact, no, integral and sum can be interchanged, right? Is that correct?
Yeah.
Also look at your
Yes.
notes if you don't remember. Integral and limit can be interchanged. And which sum did we apply this to? Is it the characteristic function of ANs?
Yes, sir.
Did we consider summation chi AN?
Chi N, yeah.
And integral of summation chi AN is summation of integral chi AN, which is summation of mu AN, which is given to be finite, right?
Finite. Yes.
And so if integral of summation chi an is finite, yeah, this is good. And that means what? Yeah, so first of all, we have to show something has measure 0. So that set has measure 0. And we interpreted, and there was one more idea, no? We interpreted it in terms of a function taking values infinity, right? If this function is infinite, yeah. So this summation chi an, if it is infinity, what does that mean? Summation chi an, this function, if at one point, if it is infinity, that means x belongs to infinitely many
Infinite
ans, right?
N, yeah.
So this function, so whenever x belongs to infinitely many ans, then this function will be infinity. But by doing this thing, integral of this function is finite. What is the conclusion? If integral is finite, then set
Measure
of
of that set
points
is
where,
0.
yeah, set of points where the function takes a value infinity has to be of measure 0, right?
Measure, yes.
Otherwise, integral cannot be infinite. Integral cannot be finite. So that's the proof. So set of points where x belongs to infinitely many of these sets, that is measure 0. That's a claim, no? That's what we wanted to show.
Yes, sir.
Yeah, because x belonging to infinitely many of these things is same as saying it belongs to the intersection of the union, right? Union from k to infinity, and then I going from k to infinity. That is like the supremum, and then you take the intersection of sup. Correct? You wanted to show that almost all x belong to at most finitely many sets. That was the claim, no? So that set as measure 0, we use, main idea was just interchanging. So that was Borel-Cantelli. That's also a very famous result. And today we will do some topological preparation for RRT. As I said, maybe you know all these things already, but it's good to recall. And then, we are going to construct Lebesgue measure. What is Lebesgue measure? What is the Lebesgue measure? You might have done it for R, but maybe for Euclidean spaces Rn, what is its property? What is Lebesgue measure on R? What are the properties? Maybe I'm not asking for all the technical properties which we have not discussed, but what is most striking?
If some set as measure 0, if I found a subset, then it should be also measure 0.
Yes, so it is a complete measure, of course. But what is the most striking aspect of Lebesgue measure?
Lebesgue measure of intervals is length of that.
Of course, but what is the most important property of the Lebesgue measure? See, there are many measures that you can construct, but Lebesgue measure has a very important property, right?
Sir, it is from outer measure, and then
Yeah, so maybe some regularity conditions are there, of course, but there is something which is even more striking. See, many measures may have these regularity properties, but something which is even more striking.
Translation
Yeah,
invariant.
it's translation invariant. Okay. And on R and on Rn and all, we can easily do this construction of Lebesgue measure using Riesz representation theorem. I don't know how you would have done it in MSc, but this is how we will do it. And more generally, there is nothing important about real line. All that we are using is there is translation, there is a group structure, there is addition, and also topologically it is locally compact. Right, real line is locally compact, Euclidean space Rn is locally compact. So if you have any locally compact group, any group, and then you can construct a translation invariant good measure, a Borel measure, which is called the Haar measure. How many of you have heard this word Haar measure? Just heard. I'm not asking whether you know it.
I have heard it, but I don't.
Okay. Okay. So Haar
I
measure.
also heard.
Yeah. So Haar measure is the analog of Lebesgue measure for more generally for any group. The topological condition on the group is it should be locally compact. It's a topological group. What is a topological group? It should be a group. It should also be a topological space, and there should be compatibility. What is compatibility? The group operation should be
continuous.
continuous. So where is the group operation? It's a map from G cross G to G, right? And that should be continuous. G cross G will have the product topology. And inverse is a map from G to G, that also should be continuous. Okay. So, and if the topology is locally compact, then there exists a measure which is translation invariant. Translation you can ask for whether from the left or right, because the group need not be commutative. So translating on the left and translating on the right are two different things, but The claim is there exists a left invariant measure or right invariant measure. Okay, one of those. So this is a consequence of RRT. We will see. And one remark before we start is that whenever in Rudin he uses the word neighborhood, he always means it to be an open neighborhood. He may not stress the word open, it is understood. Okay, so let's start. So this doesn't have a name, so I have given the theorem number. You have a topological space X, and you have a compact set contained in an open set. Okay, K is compact and U is open, and X has some property. X is of course Hausdorff, and it is also locally compact. What is locally compact?
Every point has a compact neighbor.
Yeah, every point has a neighborhood whose closure is compact neighborhood. Okay, so we will not say compact neighborhood because for Rudin neighborhood means open. So in what you said is correct, and our way of putting that will be every point has a neighborhood whose closure is compact. And in a Hausdorff space, what is Hausdorff? Any two points can be separated, right?
Yes.
Given two distinct points, there are one open set containing this, other containing that, which are disjoint. Is it true that a compact set and a point can be separated?
Not necessarily.
No, in a Hausdorff space, given a compact set and a point, disjoint from that, can you separate it?
Yes, I think.
You can, right? Because using compactness. What will you do?
We will construct a disjoint set
Yes.
corresponding to all points on that
So
compact.
first of all, this compact set can be contained in a finite union of open sets, right? And you can cover it by balls, and from that you can extract a finite number, and for each of those you can separate this point outside, and maybe you can take union or intersection or some such thing, right? And finite union of compact sets, no, finite intersection of open sets is open. That's all that you need. So
Yes.
because of compactness you can do that. We are going to use it, and the K is compact, U is open. And the first claim is that whenever you are in this situation, because of local compactness, whenever you have compact contained in open, I can find an open set V with the property that its closure is compact. V is open and V bar is compact, sandwiched between K and U. Okay, between K and U, I can put a V contained in V bar. V bar is a closure, the smallest closed set containing V. And this can always be done. Have you seen this result already in your topology class? Anyway, it's not hard, it's elementary topology. So let's do that. So every point in K has a neighborhood with compact closure. Why?
Locally compact.
Because locally compact is given to you. And by the compactness of K, it can be covered by finitely many of these, right? Because every point has a neighborhood. All these neighborhoods together will cover it. That's an infinite cover possibly. And you can extract a finite subcover by compactness. And you take closures of all this. Yeah. So it's a finite union of. So if V1, etc., Vn you have, you are taking V1 bar union Vn bar. Can you, is that compact? If you have A and B two open sets, and if you take A bar union B bar, is that compact? Yeah, A bar is compact, no? If you have a set A, and if you take bar, A bar is compact, right? Why is A bar compact? Why are you not responding? If you take a set A and if you take its closure, I'm saying it's compact.
In a compact space.
So, yeah. So correct. So, uh, yeah. So in this case, it is given to you that every point has a neighborhood with compact closure. So A is such a set. A is a neighborhood whose bar is compact is given to you. A bar is compact. Now if you have A and B and A bar is compact, B bar is compact, then A bar union B bar is compact, right?
Yes.
Finite union of compact sets is compact. So by taking this, you get a set called that union G. G is open and G bar is compact, right? So G is A union B, finite union, but suppose it's A union B, then what is G bar? If G is A union B, what is G bar? G bar is A union B bar, but that is same as A bar union B bar, right? No?
Yes.
And that is compact, finite union of compact sets. So such that K is contained in G and G bar is compact. So this will solve the problem if your U was X itself. Right? You have K contained in U contained in X. K contained in U contained in X. If U was X itself, then you could have taken V to be G. Because you have got G open, G bar compact, G contained in G bar contained in X. So if U is X, you have already solved the problem. But U may not be X, and then we have to do a little bit more work. So let's do that. So first of all, as you observed in a Hausdorff space, a compact. Can you hear me clearly, or there's a lot of disturbance?
So there is
Yes,
some
sir.
background noise.
There's some background noise, but when I speak, what I'm speaking is clear, no?
Yes,
Yes.
Okay.
it's okay.
So in a Hausdorff space, a compact set and a point outside can be separated, and we are going to use this fact. So if U is not the whole of X, if U is the whole of X, we are done. Okay, if U is the full set, then we are done. If U is not the full set, then take a point outside U. Take a point in its complement, and then there is a neighborhood of K with P outside its closure. Why is that? Corresponding to each point outside U, I am saying that there is a neighborhood containing K whose closure does not have P. What are you doing here?
Separating
Yeah, you are separating what?
compact set and the point
Compact set and this point P, right?
outside.
Outside this P outside U, and this compact set is contained in U, and you are separating that, and from that you will get that P is not just in WP, it's not in WP closure also, right? Limit point, it cannot be a limit point of WP. So this you have, and then you consider this collection, the complement of U, you intersect with G bar, which we have found here, okay, and intersect with WP bar. And this collection is as P varies over the complement of U. What can you say about this? What can you say about the intersection of all these sets? So this is one set, and as P varies, you get more sets. If you take intersection as P varies, what can you say about the intersection? Yeah, just from this fact, P is not in WP bar, right? If P is outside U, then there is a neighborhood WP such that P is not in WP bar. So as P varies, if you take the intersection, what is the claim? P is from X minus U, and corresponding to a P in X minus U, there is a WP bar which does not contain P. So take any point here, corresponding to that, there is a WP bar which does not contain that point. So what is that intersection?
Empty.
Hi,
Hmm?
empty set.
Empty set. So when you take the intersection, it is empty. So this is possibly an infinite collection, and the infinite intersection is empty. So, and all these are inside G bar, right? All these sets are inside G bar, no? Because you are intersecting with G bar. And what do you know about G bar? G bar is compact. So in a compact set, if you have a collection whose whole intersection is empty, what can you conclude by compactness? There is a famous property, no, with compactness about infinite intersection, I mean arbitrary intersection and finite intersection. Basic topology.
So I think for nested interval, like
You don't need nested interval, no? There is finite intersection property, right?
yes, I mean if collection of compact set has finite intersection property, then the whole intersection will be contains one
Yeah.
point.
So if every finite intersection is non-empty, then the whole intersection is non-empty, right?
Yes.
If every possible finite intersection is non-empty, then any arbitrary intersection is non-empty. So in this case, the whole intersection is empty. So therefore, there is a finite intersection which is empty. There exists. Okay, so this intersection is empty. So by the compactness, there's an empty finite intersection, which means you have P1, P2, etc., Pn, such that this intersection is empty. You agree with this? This is just using compactness. Okay. Now you are done because now you can take V to B. Can you give me V? What do we want? We want V such that V bar is compact, V is open, V bar is compact, K is contained in V and V bar is contained in U. What is V for you?
WP1 intersection WP up
Yes.
to
So
WPN.
if you take V to be G intersection WP1 etc. WPN, then V is contained in U because its intersection with U complement is empty. Its intersection with U complement is empty, so it is contained in U. So V is contained in U and V bar is compact. Agree? Why is V bar compact? Why is V bar compact?
Because G bar is compact and WP1 and V bar contained in that set.
Yes, so a closed subset of a compact set is compact, right?
Yes.
Okay. Now we are going to introduce this notion of semi-continuity. Have you seen this already in real analysis in MSc or somewhere? The notion, you know continuous functions. Do you know semi-continuous functions?
No, sir.
Yes or no?
No, sir.
No? Okay. So let us introduce. So it will be like something slightly less than continuity, right? That's why it's semi-continuous. And see, when you have the notion of limit, you also have the notion of limit inferior and limit superior. These are smaller, I mean, weaker notions, right? And the strong notion of limit will be when lim equal to lim sup. Something similar. You will have two notions of semi-continuity. One on one side and on the other side. So you will have what is called lower semi-continuity and upper semi-continuity. And continuity should be same as what is your guess. Suppose we define lower semi-continuity and upper semi-continuity in some way. What is your guess? What should be continuity equivalent to?
If
I'm
it
just
is
telling
both lower and
both, yeah,
upper.
lower and
both lower semi-continuous and upper semi-continuous. That should be if and only if continuous. So we are going to make a definition. So first of all, you take the characteristic function of a set A. Okay. F is chi A. And if you consider this collection, for every alpha, if you consider X such that Fx bigger than alpha, what are the possible choices for this set as alpha varies? Suppose alpha is 2. What is this set? Fx is chi A. If alpha is 2, what is this set?
empty set.
Empty set. If alpha is 1.5, what is this set? Empty set. If alpha is 0.5, what is this set?
A
And if alpha is -1, what is this set?
false set.
So the choices are this set can be either full set or A or empty set, right? Those are the only possibilities, no?
Yes, sir.
Okay. And what if you consider this collection as alpha varies? What are the possibilities?
Empty set A and
Empty set
one
and full set. And the other set is? Suppose alpha
complement
is
of A.
0.5, complement of A. Okay.
Yeah.
So the first set is either X or A or empty, and the second set possibilities are empty or the complement of A or X. Okay. So if A is open set, suppose A is open, then the first set is always open, right?
Yes.
If A is
Yes.
given to be open, the first set is always open, and if A is closed, then the second set is always open. Always meaning as alpha varies. Agree? Yeah?
Yes.
And what is the definition of continuity? Inverse image of?
Open set.
Inverse image of open set is open, right? And suppose you have a function which is valued either in real numbers or in extended real. Either way, set of all x such that fx greater than alpha is same as f inverse of alpha to infinity. Infinity may be closed or open depending on R or extended real, right? But that's an open set, right? So this is inverse image of a particular open set, alpha to infinity. And this is inverse image of a particular open set. Which is that open set?
F inverse of minus infinity to alpha.
Correct. Inverse image of minus infinity to alpha. That's a particular open set. So continuity would mean inverse image of any open set is open. And we are going to define semi-continuity. One notion of semi-continuity is this set is open. So inverse image of particular types of open sets. And the other notion of semi-continuity is inverse image of, these sets are open. Is that okay? So one is called lower and the other is called upper. You want to give me, it's up to us to define. Someone has to define, but suppose, I am asking you to define which will you call lower and which will you call upper. It's just your taste. Then I will tell you what is a standard definition. You could have defined either one as lower and the other one as upper. It's up to you. But let us try to remember correctly. Let us try to remember the textbook definition. So what do you say? Which is lower, which is upper? It's not up to us. There is a standard definition which we have to follow. But I'm just trying to see whether you will get the standard definition if you define it on your own. So as I said, this is inverse image of alpha to infinity, and that should be open. This is inverse image of minus infinity to alpha, and that should be open. One of you can just tell me something. There is no right or wrong for this question. Whatever you say is one answer. Which one would you like to call lower semi-continuous?
F of x less than alpha is lower, man.
Okay. And of course, then the other possibility is that you call upper. And the only reason why I'm going slow is that whatever is the definition, you should remember it correctly later. And who said this? This should be lower?
Samarendra, but I did not know. Yes.
No. I'm just saying that Samarendra, now you will not forget. You just have to remember that what you said is not correct. Okay, then you will get the correct definition.
I'm not clear.
Yeah. So no, there's no way to guess or anything. I just wanted to talk about it so that you will remember. Okay. So a function is said to be lower continuous if the first set is always open. If this is always open as alpha varies, then you say that the function is lower semi-continuous. And in particular, characteristic function of which sets are lower semi-continuous, open sets or closed sets? Characteristic function of open sets are lower semi-continuous automatically. Okay. And now you know the definition of upper semi-continuity. I don't have to write it. And characteristic function of which sets are automatically upper semi-continuous?
Closed sets.
Closed sets. So similarly, upper semi-continuity and characteristic functions of closed sets are upper semi-continuous. Here is one way to remember which is lower, which is upper, right? It can always be confusing, no? To remember which is lower, which is upper. Either you remember that for open
Yes.
set is lower, but again, how will you remember that? Right, there's no way to remember much later. No, open is lower and closed is upper. You might get confused. Closed is lower, open is upper. So one way to remember this, I mean, this is how I try to remember. There's one more way which I will show in the next slide, which I took from Wikipedia. But the way I usually remember is first set as we said, f inverse of alpha to infinity. Out of alpha and infinity, which is the variable and which is fixed?
Alpha.
Infinity is anyway fixed, right? So alpha is a variable, and this is lower semi-continuity. We know that is a standard definition, and the variable is at the lower end. Lower meaning left, right? So variable is at the lower end, and that is lower semi-continuity. That's a good way to remember, no? You know that you have to take alpha to infinity or minus infinity to alpha. In one, the variable is at the lower end, and the other variable is at the upper end. And when the variable is at the lower end, it's lower semi-continuous. Okay. So if fn's are given to be, you know, a collection, I'm not saying n is a natural number, any arbitrary collection. And suppose fn's are lower semi-continuous. Can you say that the supremum is also lower semi-continuous? So how will you check? So you have to check the set of x such that fx is bigger than alpha. But what is that set?
Union of
Union of fnx is bigger than alpha, and all these are given to be open. Arbitrary union of open sets is open, so this is fine. And similarly, if fn's are upper semi-continuous, can you guess what is upper semi-continuous? So you will take x such that fx is less than alpha, and that should be a union of x such that fnx less than alpha. So what is that function? What is f? Right? It's always about open sets. So you should get union in order to conclude union of openness open. So if fn's are upper semi-continuous, can you guess what is upper semi-continuous? Anyway, if this result was about soup, what will be the next result?
infimum of fn.
Yeah. So infimum is upper semi-continuous because if G is the infimum, and if you take x as at gx is less than alpha, then how is this related to fnx is less than alpha? If infimum is less than alpha, then at least 1 is less than alpha, no? So this is also union, right? Agree? And if x belongs here, then at least one fnx is less than alpha, and therefore infimum is less than alpha. So this is okay, right? So this is openness upper semi-continuous, union of openness open. So this is upper semi-continuous. Okay, we are going to use all these things soon. So obviously a function is continuous if and only if it's both lower semi-continuous and upper semi-continuous. Is that clear? Because if it's both lower semi-continuous and upper semi-continuous, then f inverse of this open sets are open, and f inverse of minus infinity to alpha is also open. Therefore f inverse of any open set is open, no? Any open set will be a to b, that is minus infinity to b intersection a to infinity. Agree?
Yes.
So that's okay. And here is another way of remembering which is lower, which is upper. This I saw in Wikipedia just yesterday. If we take a continuous function, just take from real line to real line, r to r. And if you take a continuous function and increase its value at one point, okay, you are just at one point, you know, erase the original value and just arbitrarily increase. Of course, continuity is lost, no, in your graph.
Yes.
Continuity is lost, but it is upper semi-continuous. Verify. Easy to verify. Okay. So when you increase its value, the semi-continuity that you are retaining is upper because it's increased. Okay, that's one way to remember. Similarly, if we decrease its value at one point, then according to our definition, the resulting function is lower semi-continuous. So I'm assuming singletons are closed, so that if you have an open set and if you remove one point, still what you get is open. Okay, so if the singletons are closed. Singletons are closed always in a Hausdorff space, no? Is that true? Yeah?
Yes, sir.
Maybe you don't need Hausdorff, right? Singletons are closed itself as a separation axiom, no? What is it called? T1? Whatever. Anyway. So we will always be on Hausdorff spaces. Okay. Now, you know, when a function is said to be of compact support, what is the support of a function? Set of all points where
F of
Not
x.
zero.
f is non-zero, and typically we take the closure. Okay, so support of f is this, and when will you say a function has compact support? If this set is compact. Okay, so CCX is defined to be all those functions which are continuous of compact support. This C is for continuous and this C is for compact. So continuous functions of compact support. Okay, so keep this in mind. And is this a vector space? If two functions are continuous, of course sum is continuous, scalar multiple is also continuous. And what about support? If f and g have compact support, is it true that f plus g has compact support? Scalar multiplication of course has compact support, but is this true that f plus g has compact support? What can you, how is support of f plus g related to support of f and support of g? Forget the bar. Suppose you know that fx plus gx is non-zero. That said, how do you relate it with fx non-zero and gx non-zero? So if you have set of all x that fx plus gx is non-zero, then that's a subset of the union of those two sets, right?
Yes.
Yeah.
So you can take bar on this. So bar of this will be A union B bar, which is A bar union B bar. And A bar union B bar is compact because it's a finite union of compact sets. And this is a closed subset of a compact set, and therefore this is compact. So that's enough, right? So this is a vector space, and you can check that. We have already checked. And if f is in CCX, then I claim that the range is compact. Is that correct? If f is of continuous function of compact support, then f of x is compact. Basically, what are you using here? Continuous image of a compact set is compact, right? That's correct, no? Continuous image of a compact set is compact, right?
Yes.
So basically that is the idea, but how do you actually show this? So fx you can write as, if x itself is compact, then of course fx is compact, right? So there's nothing to check. If x is not compact, then you make the observation that if x is not compact, then you make sure that f of x is nothing but f of support of f union singleton 0. So support of f is compact, and this is continuous image of a compact set. So this is compact. Singleton is closed and therefore compact. So singleton is anyway compact, and this is union of two compact sets, therefore this is compact. So the point is, if x is not compact, then 0 belongs to fx. It's easy to check. You can check that. So f of x is compact. Now we are going to do Urysohn's lemma. I hope I have time. And you have already seen a proof of Urysohn's lemma in MSc. Anyway, let's do it as Rodin does in this generality. We will have frequently two notations. One is, so what is K always? If I don't say anything, what is K?
Compact set.
Compact, and U, V, etc. are open sets. And you have this notation. I don't know what to call it. The text symbol is preceding, press /prec. So let's say preceding. K precedes F. And you can have a notation of succeeds also, but we are going to do only K precedes F, and also F precedes V. V is open, K is compact. So what does this mean? This notation means K is always compact, V is always open. K precedes F, meaning F is in CCX. It's a continuous function of compact support. Values are between 0 and 1. This much is understood. Okay, we will not repeat this. When we write this notation, it is understood that F is in CCX and fx is between 0 and 1, and why is k playing a role? This means f is identically 1 on k. Is the notation clear? F is always in CCX. It takes values between 0 and 1. And if we write k precedes f, f is identically 1 on k. Similarly, when we write f precedes v, all these conditions, f is in CCX, fx is between 0 and 1. But this notation meaning support of f is contained in v. Okay. So when we write k precedes f, f is identically 1 on k. And when we write f precedes f, support of f is contained in v. Okay, these are two notations. And with this notation, we will state Urysohn's lemma. So Pavel Urysohn, only yesterday it struck me. Look how young he was when he died. What was his age when he died?
26.
26. So I was curious, how come such a small age? So what do you think? Natural accident, a natural or accident? If you have to take a guess, of course, one can have an illness also. Yeah, did you say something? Natural or accident? Young
Maybe
age.
some accident.
Yeah, so I only yesterday I read about him, and he was a very brilliant student, and he was visiting somewhere, and he used to swim in swim in the ocean. So in one of those things, he drowned. So it's an accident, one of a swimming accident. So anyway, very useful result. So the formulation as in Rudin is, you have a locally compact Hausdorff space, and you have k contained in v contained in x. So what is k? K is compact and v is open. And already with k compact contained in v open, we already have a result. No, can you state that result? Because that result will be frequently used in this proof. If you have k contained in v, k compact v open, what is the result that we proved sometime back? The first result that we proved today.
There exists a open set
Whose
between
closure is
K and
compact between k and v, right? And we are going to use that many times. But the claim in Urysohn is there exists an f such that k precedes f and f precedes v. So what is the meaning of this? There exists a continuous function of compact support f whose values are between
0 to 1.
0 and 1, and on k it's
1.
Identically 1. And regarding v, what is the claim?
support of f is contained.
Support of f is contained in v. This kind of a continuous function is guaranteed is the Urysohn's lemma. So in particular, the way to intuitively, the one way to think about Urysohn's lemma is that it supplies plenty of continuous functions, right? You are putting some strong conditions and you are saying still there is a continuous function satisfying those. So, right, we discussed this at some point, no? What was the word? When did we mention all these things? I think somebody mentioned Hahn-Banach theorem and I mentioned Urysohn. What was the context in lecture 1 or lecture 2?
Separates.
This is not quite separate. I think I made a mistake. I used the word separate, but what was the basic English idea? I mean, English sentence.
It exists a lot of.
Yeah, exists a lot of it. So in some way we have to claim, and sigma algebras exist in great profusion was Rudin's sentence. And I said Urysohn also, is some kind of a result because you put some strict conditions and still it says there is the continuous function satisfying that. So in other words, continuous functions, there are lots of continuous functions. Same with Hahn-Banach theorem, right? It says, a continuous linear functional can be extended as a continuous linear functional with minimal hypothesis. So therefore, plenty of continuous linear functionals exist on a non-linear space. Okay. So recall that this means f is in CCX, f is between 0 and 1, f is identically 1 on k, and support of f is contained in v. And in other words, in terms of characteristic functions, how can you reformulate this k precedes f precedes v? Can you state it in terms of characteristic functions? F is bigger than or equal to the characteristic function of k and f is less than or equal to characteristic function of v. There exists a continuous function such that chi k is less than or equal to f less than or equal to chi v. You agree, right? Because f is anyway between 0 and 1 and continuity is given. Continuity is there. It's anyway between 0 and 1 and f is identically 1 on k. But f is identically 1 on k is clear, no, here. Because f is bigger than chi k and chi k is 1 on k. And support of f is contained in v is also clear, right? Because f is less than or equal to this. So outside v it is 0. Outside v this is 0, therefore f is also 0. But why is f of compact support? What is the support of f? If you have a function f which is between chi k and chi v, what is the support of f? Support of f is all those points where f is non-zero and take the closure. So all those points where f is non-zero, what is that? If f is non-zero, then support is contained in v, right? F is less than or equal to chi v, so support is contained in v. And then you are taking its closure. See, here I'm saying that f has compact support and support is contained in v. Now I'm asking, just from this, can you conclude that f has compact support? Or should I say that continuous function of compact support says that this happens? That's my question. This clearly shows support of f is contained in v, and it also shows f is valued between 0 and 1. But just from this you cannot conclude, no? Support is compact.
Yes, sir, I think.
You can conclude?
No, sir, we can't able to conclude.
Yeah, you can't. Yeah. So I should say there is a continuous function of compact support between this, because what will happen is on k it is 1, so I know that support contains k and support is contained in v, but why should that set be compact? Yeah, maybe I have to add that. I will think about it. Okay, so it is, yeah, this is the point to remember. It is a continuity that is the most important thing here. Because if you were interested only in semi-continuity, then of course you have such functions, right? You could have taken chi k or you could have taken chi v. Chi k satisfies this, no? Chi k satisfies this because what is the support of chi k? Support of chi k is k, which is compact, and it is 1 on k, and support of f is contained in v is also true. And what if you take chi v? What is the support of chi v?
V closure.
Support of chi v is?
V closure.
Chi v is 1 on v and 0 outside. Yeah, it is v bar. V bar. And
Sir, support is set of all x such that f of x not equal to 0, right, sir?
no, closure of that set.
Sir, for compact only we will think closure.
No, our definition of support is this. For any function, this is a support.
Okay,
So
sir.
if you have characteristic function of v, then set of all x's at chi v x is non-zero is v, and bar is anyway there. So it is v bar. Support of f is v bar.
Okay.
So v bar is so support is always closed by definition. Yeah, so maybe here also I should be a bit careful, because I cannot say chi-V is of compact support, right?
Yes.
But yeah, I cannot say that. But other than compact support, all other properties are satisfied. Let me just double check. Maybe the point is, this is, even if there's a mistake in what I'm saying, in practice there's no mistake, because in practice we will always work with, if you are in such a situation, we will work with that thing in between whose closure is given to be compact. Right? That lemma, no? If you have K contained in U, then there is a V such that K is contained in V is contained in V bar is contained in U, and V bar is compact. This is where we practically will apply things. Okay. So V bar compact is, we will be mostly in a situation where V bar is given to be compact. I mean, the V will be such that V bar is compact, but not in general. So I will make the appropriate changes before uploading. So let's prove it. So it's first thing to remember is it's quite an ingenious, very nice proof. So let us see the basic structure of the proof, and I will leave the details for you to work out. So the thing to remember is you are going to have a collection of open sets. Does anyone remember the one or two key words in the proof from MSc? If you recall, what is one important thing that you remember about the structure of the proof? If you see the proof, there will be one or two things that you will remember, or you can remember. Anyone remembers this proof? I mean, at least one or two key concepts in the proof. Okay, then let me say that we are going to list a collection of open sets. All those compact sets, all those open sets, the closure will be compact. So we will use that observation in order to construct those. And how many open sets are we going to list? It will be a countable collection and parameterized by rational numbers in 0, 1. Do you remember this idea? So we will have an enumeration of rational numbers, and we will use that, and for each rational number there will be exactly one set in this collection, and this collection will have, so the collection is, let us say Vi, where I is a rational number in 0 and 1, and this will have the property that K is contained in V1, which of course is contained in V1 bar. V1 bar is contained in V0, which of course is contained in V0 bar, which is contained in V. K and V are given to you, right? And you're going to construct V1, V1 point, V.5, all these things you're going to construct with this property and with this extra property that whenever S is bigger than R, remember V1 bar is contained in V0. And this is the property. Whenever S is bigger than R, Vs bar is contained in VR. Okay. Suppose you have constructed this. This is the first thing that we should do. You have to construct open sets. Closures are compact with this property. Whenever you have a bigger number, the appropriate open set, the bar is contained in the other one. And once you construct this, you are going to consider a sequence of functions. So given a rational number in 0, 1, fr of x is R if x belongs to VR and 0 otherwise. Is it like a characteristic function? It's almost like a characteristic function, right? What exactly is fr in terms of characteristic function?
R times
R times VR. So is it semi-continuous? VR is open. So characteristic functions of open sets are
lower semi-continuous.
Lower semi-continuous. So all these FRs are lower semi-continuous. Agree? All these FRs are lower semi-continuous. And consider GS to be 1 if X belongs to VS bar and S otherwise. And you check. You check that all these GS, this is not characteristic function, but still, you can check from the definition that GS are upper semi-continuous. Okay? How is FR and GS related? Can you say FR is less than or equal to GS, or FR is bigger than or equal to GS, or something like that? Can you compare FR and GS? Is there an inequality between them? See, given two numbers R and S, what are the possibilities? Given two distinct numbers R and S, either R is less than S or R is bigger than S, right? If R is less than S, how are FR and GS related? If R is less than S, FR is R or 0. And GS is 1 or S. R and S are less than 1, right? It's enumeration inside 0, 1. So
Yes.
R is less than S. R is also less than 1. So if R is less than S, then clearly FR is less than GS, right? Agree?
Yes.
If R is less than S, clearly FR is less than GS. What if R is bigger than S? If R is bigger than if R is bigger than S, what is the relationship between VR and VS? Which is smaller? If R is bigger, then VR is smaller, no?
Yes.
That's how we are constructing, right? If R is bigger, then VR is smaller. So if R is bigger, then VR is contained in VS. VR bar is contained in VS. So in particular, VR is contained in VS bar, and R is less than 1, no? So in all cases, FR is less than GS. Agree? Always FR is less than GS. Always. Okay. So if you take, if you are in such a situation, and if FR is lower semi-continuous, which one will you take, sup or inf, so that semi-continuity is retained? If you have a collection of lower semi-continuous functions, then what was our observation? Their sup is also lower semi-continuous, right? And
Yes,
if you have a collection of upper semi-continuous functions, then their inf is also upper semi-continuous. So from this slide, can you give me one lower semi-continuous function and one upper semi-continuous function? You can take sup of FR, that will be lower semi-continuous, and you can take inf of GS, that will be upper semi-continuous. Okay? And FR is bigger than less than GS, you know that. So can you make a very good claim? See, we are going to finish the proof. If this much is done, we can finish the proof. See, what is the claim? What should we prove? We should get a continuous function. How do you get a continuous function in terms of semi-continuity?
Supremum of FR is equal to infimum of G.
Yes, yes, and that is believable, no? Because FR is smaller than GS. Out of all GS, you are taking the smallest, infimum, and out of all FR, you are pushing it up. You are taking the supremum. So you can hope that they are equal, right? Maybe they are not, but it's a good hope. Agree?
Yes.
Yeah.
Yes.
So suppose you know that claim is true. Then have you proved the result? Because sup of FR is lower semi-continuous, right? And inf of GS is upper semi-continuous. So if you prove they are equal, then that function is continuous, no?
Yes.
And that function satisfies all these properties is easy to check. Because all the FR support is contained in VR. Okay. Therefore, supremum also the support, and all these VRs are contained inside V. So supremum will also have support inside V. So that's okay. And all the GS is 1 on VS bar. And therefore the infimum, and therefore 1 on K, because all the VS bar contains K. So the infimum will also be identically 1 on K. So that's also okay. And what is the support of this function? Support of this function is, what is the support of this function? Support of FR is VR bar, no?
Yes.
That is compact. So so the support of the, so at each stage, so yeah, you have to conclude that the support is compact. Essentially, it will come from the fact that all the VR bars are compact. Yeah, you have to check that also. You can check that also. Okay. So let's see. So supremum of FR is non-zero. All the FRs are between 0 and 1. Therefore, the supremum is also between 0 and 1. And the supremum is non-zero. So points where the supremum is non-zero out of all R. So supremum is non-zero means what? At least one FR is non-zero, right?
Yes.
At least one, no?
Yes.
So you will get
Union of
union of support of FR, is it?
yes.
But support of FR is compact because that's VR bar. But do you know that the countable union of compact sets is compact? That may not be true, right?
Yes, sir.
Yes, sir.
Yes, meaning no, right? Only finite union you can claim, no?
Yes, sir.
Okay. So further, if we argue with infimum GS, also no hope, no? Because GS is non-zero. GS is always non-zero, right?
Except for s equal to 0.
Hmm?
G0.
Yeah, except that.
Yes.
So G0 is
Characteristic function of
characteristic function of
V0 closure.
V0 closure. So correct. And all the other VS bar, everything is contained in V0 closure, right? Everything else is contained in V0 closure, no? Because VS bar is contained in VR whenever S is bigger than R and everything is bigger than 0. So everything else is contained in V0 closure. So support. So can you say that support of GS is contained in V0 closure? Yes, right? That's correct, no? Support of GS is contained in V0 closure for whatever S you have. No.
No, sir.
No, that's not true. That's not true. What you know is support of G0 is V0 closure.
V0.
And so if infimum of GS, when you are looking at the support, how does that work? So infimum of GS is non-zero. So what can you say? If infimum of...
So, sir, here we can take intersection because
Yeah, here it is intersection.
so that's why that intersection will be only V0 closure.
Correct. So therefore, yeah, so therefore this is contained in, so the infimum of GS, its support is contained in V0 bar, right? It will be contained in particular in the support of G0, right?
Yes.
And that's contained in V0 bar. So you are getting a closed subset of a compact subset. Therefore, the support is compact. V0 bar is compact. It's given to us that all these VI's collection is with compact closures. Okay, so support is compact is also clear. So all the properties will be there. So this is the idea of the proof. So what is there to, what is remaining? This is the structure of the proof. So what is remaining is just this construction, no? Because the rest we have proved. FR, this is the definition, GS, this is the definition, and we have to show that this is equal. Yeah, so these are the remaining things. So here is a basic idea. This can be constructed, do you agree? This can be constructed in two steps. First, sorry. First, given K and V, I can construct a V0. Some allergy. So I can construct a V0 by that argument earlier. And given K and V0, I can construct a V1. You agree? Given any compact contained in an open V, I can construct these open sets whose closure is compact. So like that, I can construct this. Now what you do is the following. You enumerate the rational numbers R1 is 0, R2 is 1, and then the remaining you enumerate as you like, R3, R4, etc. Okay, and then what you do is, for V1 bar contained in V0, for V1 bar contained in V0, you construct VR3 contained in VR3 bar. This you can do. And now what you do is, you might construct VR4 either like this or like this. Okay. Can you tell me when will I choose like this and when will I choose like this? Because what we finally want is this one. When S is bigger than R, you want Vs bar to be contained in VR. So you check whether R3 is bigger than R4 or R4 is bigger than R3. One of the two is true, no? So if R3 is bigger than R4, you choose VR4 between VR3 bar contained in V0. If on the other hand R4 is bigger than R3, you choose R4 between this. Like this you construct. So how will you choose VR5? Can someone tell me what is the idea to do VR5? So you have to give me a compact set contained in an open set and choose in between VR5. So that depends on where R5 is in relation to 0, 1, R3 and R4. Suppose R5 is bigger than R3, R3 is bigger than R4 and R5 is bigger than R3. Where will you choose your VR5? Suppose R3 is bigger than R4 and R5 is bigger than R3. If R5 is bigger than R3, you have to sandwich R5 between two rational numbers. If R5 is bigger than R3, what are the numbers that you will consider? You can consider 1 is bigger than R5 is bigger than R3. Okay, 1 is bigger than R5 is bigger than R3, and then you take this V1 bar contained in VR3 and choose VR5 inside this by that lemma. Is the method clear? If R5 is bigger than R3, then you have 1 bigger than R5 bigger than R3 and you go for this 1 and R3 and choose R5 inside this. Suppose R4 is bigger than R5 is bigger than R3. R5 is between R4 and R3. That can happen, no? R5 may be somewhere. Suppose R4 is bigger than R5 is bigger than R3. Where will you choose VR5? Yeah. You have R4 is bigger than R5, bigger than R3. So what you do is you look at the endpoints. It is R4 and R3 and R5 is in between. So you have R4 and R3, so you go here, R4 and R3. You have a compact set contained in an open set and choose VR5 inside this by the same lemma. Okay, if you continue this process, you will always maintain this property. You will always get whenever S is bigger than R, Vs bar is contained in VR. So do this algorithm. Whenever and having chosen R5, you look at R6 and place R6 in relation to R3, R4, R5, etc. And continue this algorithm, you will get that. So that finishes that. We have already seen that FR is less than or equal to GS always. So F is less than or equal to G. You agree? F is supremum of FR and GS is infimum of GS. But FR is less than or equal to GS for whatever R and S you take. Therefore, F is less than or equal to G. What is the claim? Claim is F is equal to G. Suppose not. Suppose F is strictly less than G. Then Fx is less than Gx for some x. So you choose two rational numbers such that Fx is strictly less than R, strictly less than S, strictly less than Gx. You can do that, no? If you have two different numbers, you can choose two rational numbers in between. And now, because Fx is less than R, I conclude that x is outside VR. You agree? Because if x is VR, if x is in VR, what is FR? If x is in VR, then FR is R, right? That was the definition. FR is R. But if FR is R, then the supremum has to be at least R. Agree? supremum at x. No, that will be at least r, but fx is strictly less than r. Therefore, x is outside Vr. And similarly, from this, what can you conclude? S is strictly less than the infimum. So, if x is outside Vs bar, the answer is S. Therefore, what is the conclusion? X belongs to Vs bar. But this is a contradiction, right? This is a contradiction because if S is bigger than R, what do you know? Our construction was such that if S is bigger than R, then Vs bar is contained in Vr. So this is not possible. There's a contradiction because Vs bar is contained in Vr. So X belongs to Vs bar means X belongs to Vr. This is not possible. This is a very nice proof of Urysohn's lemma. And let me stop with the last slide. Very, very important definition, partition of unity. What we mean is if you have a locally compact Hausdorff space and suppose, K may not be contained in one open set, but what you know is K is contained in a finite union of open sets. So earlier we said that if K is contained in an open set, Urysohn's lemma tells you that there is a continuous function of compact support between 0 and 1, which is identically 1 on K and support is contained in V, right? It's an extension of that. We are going to claim that there are HI preceding VI. So HIs are continuous of compact support. And the support of HI is contained in VI, and instead of HI is identically 1, what we are going to claim is H1 plus etc. plus Hn is 1, identically 1 on K. So it's an extension of Urysohn's lemma, and it's a corollary to Urysohn's lemma actually. Is the statement clear? K contained in one open set, you had Urysohn's lemma guaranteeing a continuous function with some properties. It's an extension of that. K may not be contained in one open set, but K is contained in a finite union of open sets as given. Then if K is contained in 5 open sets, union of 5 open sets, then you will get 5 continuous functions behaving well with appropriate support such that the sum is identically 1 on K. And this is called partition of unity. This collection H1 etc. Hn is a partition of unity. Unity you are partitioning on K subordinate to the cover V1 etc. Vn. And this will play a crucial role in what we are going to do. And what is the proof? It's a simple construction. What you do is take X and K. So X belongs to Vi for some I. And our earlier observation, whenever K is contained in V, you can get this open sets inside whose closure is compact. You apply it to compact set being singleton X and open set being Vi. So what will you get? You will get an open set whose closure is compact sandwiched between these two. Call that Wx. Agree? This you can do, and Wx open and Wx bar is compact, and by compactness of K, so for every X you have got this Wx, and union of Wx is a cover for K, out of which you can extract a finite cover. And suppose you know that is Wx1 etc. Wxn. So you have got these points x1 etc. xn such that K is contained in this union. Okay. Okay, now what we are going to do is, for each I, take HI to be the union of those Wx bar which lie in Vi. K is contained in V1 union, V2 union, etc. So it's possible that Wx1 bar is contained in one of those. So take Vi and consider all those Wx whose bar is contained in Vi. Call that to be HI. Is HI compact? It's a finite union of compact sets. So HI is compact, and you can take a function Gi such that HI precedes Gi precedes Vi. Why is that true? This is the crucial step. This is because just give me one word. What is the proof? Urysohn's lemma. Urysohn's lemma is exactly that. HI compact and Vi open. So Urysohn's lemma gives you this Gi by Urysohn. Okay, now what you do is just this construction. This will do the job. Take H1 to be G1, H2 to be 1 minus G1 times G2, H3 to be 1 minus G1 into 1 minus G2 into G3 etc. Hn. If you do this, each HI support is contained in Vi is clear, easy to check, please check, and check that this sum is exactly this. And because this sum is this, you can check K is of course contained in this union, because K is contained in Wx1 etc. So K is contained in this, and you can check that the sum is 1 on K. Why is sum 1 on K? Because this sum if you take x in K, then what happens? Then x belongs to,
at least one GI.
yeah, x
That
belongs
one.
to, let us say, HI. If x belongs to HI, then GI precedes VI. So if x belongs to capital HI,
One of GY should be one in.
now what do I want? I want to say that if x, yeah, if x belongs to K, then x belongs to one of the HIs.
And
Then GI is
on
identically
HI,
one on HI.
Yeah, one of the GIs is 0, right?
no,
one
one of the GI
of the
will
GI
be
is
1.
one.
One of the GIs will
One
be
in
1,
HI.
exactly. One of the GIs will be 1.
So the product will be
Because HI precedes GI, so GI will be 1 on HI, and if something is 1, you are subtracting that, so that part, this product, one of them will be 0, therefore the product will be 0, so answer is 1. So that finishes the proof. So this is the proof of partition of unity. It's a simple consequence of Urysohn's lemma. We have exceeded time, so let us stop here, and I will stop sharing the screen. Any quick question or comment? I can also stop the recording. Yeah, so I will stop the recording, and